Hello, this lesson is going to be on Bohr's model of the atom. This is another lesson on the development of the quantum mechanical model. In the previous lesson we looked at quantized energy and the developments of Max Planck and the development of that idea of quantized energy, and how Einstein took that idea and embraced it and actually used that idea to explain the photoelectric effect. So, scientists are all in a scatter trying to figure out what to do with this information, and another young scientist, and notice what's happening here is a lot of these young scientists are coming up and they're making some changes here. They're thinking differently than the old people. They're kind of coming in with new, fresh ideas and bringing some new life into the field of physics. Now, this is a Danish physicist named Niels Bohr, and what Niels Bohr is going to do is he's going to continue on with this idea of quantized energy. He's going to take this quantized energy idea and take it one step further than Einstein did with adding it to the light. What Bohr suggests is that the atom is made up of electrons that are in distinct orbits. Now, if you remember, Rutherford never said anything about the electrons. He had left it with the nucleus being the center of positive charge, and he didn't really say anything about the electrons and where they were at. So there's a lot of question as to why the electron didn't just get pulled into the nucleus. Well, Niels Bohr was one of the first people to come up with a reasonable answer for that. What he suggested was that just like the planets are revolving around the sun without being pulled into the sun, he said the electrons are moving around the nucleus in orbits, which we also call energy levels. So he said that each of these orbits has a particular amount of energy, and he designated them 1 and 2 and 3, 4, 5. Okay, this is very similar to the planetary system, with the sun being the center and the planets going around in rings. Now, it's a nice idea and it's a pretty cool model, but the problem is it just isn't going to work, and you'll see why when we get into the Heisenberg uncertainty principle. But even though it doesn't work, it's a very remarkable model because Bohr was one of the first, the first person to quantize the energy of the electron, and that actually is the correct part. Anyway, so let's take a look at this. We say that electrons sit in the first energy level, which is closest to the nucleus. He designates it n equals 1. Now that's referred to as a ground state electron. Now we're going to stick with hydrogen as the element that we're going to investigate here, and this is what Bohr was working with. He was working really with hydrogen and tried to use his model for other elements, and it kept falling apart. So each energy level has a designation, n equals, and it's going to be a whole number, 1, 2, 3, 4. So this is where the energy is quantized. There's no halves, 3/4, or anything like that. We're just either at first energy level or the second energy level. And this is where the strangeness comes in. So if electrons, we go back to that little ring model there, if an electron is sitting in this first energy level, well, it has to stay in that energy level until it has enough energy to magically pop in over here. So the electron has to disappear and pop into the second energy level. There's no in-betweens. The electron doesn't slowly move up to the next energy level. It has this energy, and then boom, it has this energy. You continue to add energy to it, and it drops to, or jumps to, the next energy level, to n equals 3. And it keeps doing this jumping from one state to another. This is what we call excited electrons. Electrons are gaining energy and becoming more and more excited and going further and further out in the structure of the atom. So we can keep doing this until the electron is completely removed from the atom. So it is an infinite distance away from the nucleus. And yes, I did draw that way over here. Okay, so that electron will be considered removed, and that's what we call ions. Okay, so that's when the electrons are lost. So that's the idea of quantized energy. This is called a quantum leap, when the electron jumps from one spot to another and doesn't exist in the middle. Okay, again, it's not an idea that scientists really liked in the beginning, but it seemed to make sense, and you'll see why in just a second. So as an electron increases energy, it gets further and further and further from the nucleus. I think it's really important to start thinking about this now, because the electron is being held in the nucleus, or sorry, in the atom by the nucleus. And this is going to have a huge impact on how we look at trends on the periodic table, how we can describe how ions form, why there's acids, why there's bases, and so many properties are going to be held on this idea of the pull of the nucleus and the energy of the electron. So electrons in their lowest energy level are considered ground state. As they start to increase in energy, they become excited state. Okay. What is it? Outside energy is required. Okay, so it is, I'm saying you have to add energy to do this. Now you'll have seen me do a demonstration in class where I actually heated up the elements. Well, they were in excited states. Okay, and then they relax back down to ground state and they released energy. And that's what Bohr is going to do in just a little bit. He's going to actually calculate that energy. So the equation that he uses for this, and this is just for a single atom of hydrogen, is this equation right here. Now, little note, this is not on the AP test, so I don't think they're going to actually have you calculate these energies, but it's a good idea to practice and to get an idea of what to do with these. So this here is the energy of that orbit. That's what this equation is calculating. So he's calculating what that first orbit's energy is, what that electron's energy is going around the nucleus. N is the, of course, energy level that we're referring to. So what Bohr did was he meticulously calculated all of these energies. So he calculated n equals 1, n equals 2, n equals 3. So that's what this here, this represents the first energy level, second energy level. And he actually calculated each of those using E equals, or En equals, the negative 2.178 times 10 to the minus 18 joules per over N squared. Okay, so he used that to calculate each of these numbers here. Notice what happens, a huge jump in between n equals 1 and n equals 2, and then the space gets smaller and smaller and smaller and smaller. There's going to be a consequence of that a little bit later. And when n is equal to infinity, essentially that the electron gets an infinite distance away from the nucleus, we approach the energy of the electron being 0, because it's going to start to have less and less. It's not going to be interacting with the nucleus at all. So the electron is considered removed from the atom at that point. Okay, so what he did was he not only calculated that, but he also calculated the difference in energy. Okay, so this is important here too, because he final minus initial, just like you did in physics. Okay, so what Bohr did is he actually calculated and said, okay, if I have an electron in n equals 2 and it moves to n equals 4, so initially the electron is at n equals 2 and it goes to n equals 4, he's going to calculate and figure out the difference between those two energy levels. Okay, and then what he can get is an energy. Now this is a change in energy, not the energy of the electron sitting there static. Nothing happens if the electron stays in the energy level. What he calculates is how much energy it either takes for the electron to move up to that energy level, or the energy for the electron to release, that will be released when the electron drops back down to that energy level. And that's what this represents here. So this would be your change in energy level right here. So this would be your change in E from here to here, or from 2 to 4, whatever you want to calculate. Now the reason why there's such a big difference between this one and this one and this one is because in this energy level, the electron in the first one is really close to the nucleus. So it takes a lot of energy to get that electron into the second energy level. Now the electron already has energy, and it's already a little further away from the nucleus, so therefore it's going to take less energy. Further from the nucleus, already has energy, less energy, so on and so forth as you go up and up and up and up. So keep that in mind. The nucleus is pulling these electrons. So down here, what he calculated was this energy. So these lights that are coming out of here were connected to this equation right here. And this is brilliant because when he calculated this, these energies matched perfectly. So this one right here matched the line spectrum for hydrogen absolutely flawlessly. I mean, it was right on the money when he did these calculations, which shows that there must be something true to quantized energy, that this energy must be quantized in some fashion for this to be working. Again, you need an experiment to back up what you're talking about. It's one thing for him to come up with this crazy idea of the electron being quantized energy, but it's another to actually have experimental data to back it up, and that's what the line spectrum do. So Bohr was able to use quantized energy of the electron to explain the line spectra that we see. Okay, that was the brilliance of what he did. So this change in E can be equal to Planck's constant times nu. And remember that speed of light equation, we can take that back and calculate our wavelengths and our frequencies, which correspond to the electromagnetic spectrum. Absolutely brilliant piece of science here. Anyway, so let's take a look at the last little follow-up here, which is the data. So these are some important points about Bohr's model. First, it quantized the energy of the hydrogen atom, basically quantized the electron. It accounts for the line spectrum of hydrogen, which was just right on the money, but as soon as you started doing helium and lithium and all these other elements, the model started to fall apart. So he was onto something, but he wasn't quite absolutely sure where he was. And it's because he had these circular orbits. He assumed that the electron was a particle. What's called a point particle means it's a point in space. And the more negative, I wouldn't worry too much about this one. you're not going to worry. They're not going to ask you any questions about that. But it's just the idea that the more negative, the more tightly. So the higher the negative number, the more it's closely bonded, because that's the energy that the electron has to overcome. Okay, so I wouldn't worry too much about that one. And as the electron is brought closer to the nucleus, there's energy released. So as it gets closer, more energy is given off. Okay, and in the next lesson, we'll start to actually show you more faults with Bohr's model and actually show you some corrections for it. I don't know why we said we there, but it's just me, so I'll explain that. All right, talk to you later.